Millions of shallow lakes and ponds occur in lowland areas and floodplains, and they are the most abundant freshwater ecosystems throughout the world. Artificial shallow water bodies are also very common and have been constructed throughout history for many purposes. As a category of inland water ecosystems, shallow lakes and ponds are limnologically diverse, but they also have a number of features in common. Relative to deep lakes, loadings of nutrients are proportionately higher, losses are lower, and rates of nutrient recycling are faster in these shallow waters. Shallow waters are often well mixed in summer, and thus there is a tight connection between the water column and the sediments, and between the littoral zone and the open water region. Light penetration to the sediment surface can potentially support the growth of submerged plants or benthic algae over much of the basin. Relative to their small size and volume, shallow lakes and ponds host a disproportionate taxonomic and functional richness. Collectively, they represent hotspots of biodiversity at the landscape level, and even temporary water bodies support diverse communities of microbes, plants, and animals. The community dissimilarity among lakes and ponds, beta diversity, is high even at regional and local scales. This is related to the high variability in local abiotic filters, and to further species sorting via biotic filters. Different anthropogenic activities add new filters or modify these natural filters. The potential connectivity and dispersal with other lakes and ponds also affects their alpha, beta, and gamma biodiversity. Dr. Mariana Meerhoff is a professor of limnology at the Universidad de la República in Maldonado, Uruguay. Her research is on the functioning of freshwater ecosystems and their responses to human activities. She has a special interest in the ecosystem functioning of shallow lakes and ponds. And here she introduces some of the ecological features of shallow water ecosystems.
At the local scale within a lake, 4 zones can be recognized: the benthic, the pelagic, the littoral, and the riparian. In shallow lakes and ponds, energy, matter, and information, that is genetic variation, is widely exchanged between these habitats. The littoral zone is defined as the lake area that is shallow enough as to allow the growth of submerged plants, and it typically represents the highest complexity. This habitat complexity is mostly provided by aquatic macrophytes of different life forms. In one of our early experiments, we tested the effects of plant architecture by placing artificial replicas of submerged and free-floating plants in similar shallow lakes in the temperate and in the subtropical zone. We found significant effects on fish populations, macroinvertebrates, and periphyton, both in the nature and in the magnitude of such effects.
From the earliest work of Lindemann onwards, shallow lakes and ponds have been of great theoretical interest as model systems to understand ecosystem processes, including ecological responses to environmental change. In general terms, changing environmental conditions can potentially lead to ecosystem change in a smooth, continuous way. Or there may be a threshold response where the ecosystem shifts across a tipping point to a new state. Or there may be shifts among multiple states. In shallow lake ecosystems, there can be a striking pattern of regime shift, from a state of clear water and dominance by submerged macrophytes to a contrasting state of turbid water and dominance by phytoplankton. Back to Professor Meerhoff, who describes some of the causes and consequences of these changes.
The stability of each of the alternative regimes or states relies on the occurrence of different stabilizing mechanisms that can be biological, chemical, and/or physical. When there is a regime shift, species diversity, functional diversity of key components of trophic webs change, and that further promotes changes in ecosystem structure and in ecosystem functioning. Such regime shifts can have profound, even catastrophic effects for certain biological communities. Also, shifts can be catastrophic for the ecosystem itself, and therefore there is a strong need for predicting the critical values or thresholds before such a shift happens. Those can be values in pollutants or nutrient loading, for instance. But despite a considerable amount of research, predicting or finding those values has proven extremely difficult.
Many anthropogenic impacts act in combination on shallow lakes and ponds, with unpredicted consequences due to potential additive effects or synergy. On a global scale, eutrophication remains the most pervasive impact, and these perturbations continue while new threats are emerging. The effects of climate change are increasingly clear at different spatial scales and at different levels of biological organization. This combination of multiple stresses has underscored the urgent need for restoration and conservation strategies. The widespread decline in biodiversity and water quality has triggered many efforts to restore shallow lakes, mostly from eutrophication. The key ultimate measure is to reduce external nutrient loading. Higher biodiversity and lower carbon emissions may be a side effect of successful restoration. From the poles to the tropics, many shallow lakes and ponds have already become saltier or have disappeared due to climate warming and water extraction. Many more are expected to disappear or change dramatically in the coming decades. Eutrophication and climate change are expected to interact, leading to a loss of biodiversity, increased cyanobacterial blooms, and changes in water quality. Conservation of these resources will require attention to outcomes, implementation, planning, and cross-cutting issues. Both local and global actions are needed to protect these species-rich ecosystems and their ecosystem services from future change.